Hi, and welcome to this talk today on 10 things Rust could learn from Java and 5 things Java should probably steal back. I'm Scott Gerring. I have been writing Java since Java 5, and for anyone else who's been writing Java that long, surprise, we're really old now. And these days, I write a lot of Datadog, both for a bunch of fun side adventures and also for my work. I write a lot of Rust. Also for my work at Datadog. Out of curiosity, who here knows about Datadog, or Datadog as everyone else in the world pronounces it? Cool. For everyone else, we do observability for your applications and infrastructure. There's not much of that in this talk, but if you're interested, come and twist my ear about it later on. I'm happy to talk about it. And for today, we want to be talking about how Rust and Java differ from each other and where they might learn from each other. And for that, I find it helpful to have some real concrete example to talk through. Because I've spent a bunch of time in past lives working on imagery hosting systems for various exciting reasons, we're going to be doing that today. So think about something like Google Maps or OpenStreetMaps. You have a slippy web map browser, and you have a service behind it that serves up tiled imagery for you. Typically, you expose endpoints to provide the tiled imagery back itself, some endpoints that provide metadata, and some endpoints that let you do uploads. The shape of these services tends to be very typical, both how the REST API looks and also in terms of dependencies. You need something to store your metadata in, which in this case we'll use SQLite for. And you need somewhere to store the imagery itself, which you would almost always use object storage for. And this is a fun domain for talking about language comparisons because it's one where people care deeply about performance efficiency. And the reason for that is basically this slide. If you do badly at a business that's trying to do web map hosting for whatever reason, and your map viewer is really slow, users come back to you and say, hey, why are we paying for this thing that looks like this and not like Google Maps, which is free? So basically, I've tried to pick a domain that I know well and that also reflects somewhere where you might, in reality, choose to use Rust, because there's a bit of an element of performance efficiency. And this is something that we've done internally at Datadog as well. So we have a bunch of systems that aggregate metrics and logs and traces about our customers' applications, and we want to get them through to alerts and dashboards as quickly as we can, basically so customers who have incidents know that they're happening without unnecessary latency. And here for years and years, we used Golang for the metrics ingestion portion of this. It worked really well, but as we've scaled with customers, we're always looking to reduce the cost of operating things and make the latency distribution a bit tighter. And we've rewritten this in Rust recently. There's a big blog that talks about all the nuance of this. But the kind of top-level takeaway from it is that by swapping this Golang thing out for Rust, we've ended up being able to do 60 times more metrics points per second within the same resource constraints. And to be clear, this isn't a normal use case. This is like a rather specialized, narrow use case, but it kind of gives you an example of what you can end up with for domains that lend themselves to this sort of tool. And there's lots of other languages around these days as well that are kind of like rattling at the doors of the Java kingdom. Rust's big thing that most of its decisions as a language fall back on is this idea of zero-cost abstractions. Let's let you, as the developer, work at a higher level of abstraction when you program, but let's do it without imposing a runtime cost. And the well-known one is memory safety. This contrasts with C, which does not have memory safety. It's good fun. You can cast void pointers to all sorts of things, and you feel very serious, but the upshot of that is that you have adventures at runtime when it all goes wrong. It contrasts with Java, obviously, where you have safety. You don't even think in these terms anymore of segfaults, but the cost is borne by the runtime. Don't get me wrong, the runtimes are absolutely ridiculous pieces of engineering, but there remains some residual costs there. And Rust's angle is basically, let's see if we can prove this safety at compile time by constraining how you write your code so that you don't have to manage memory yourself, but we can avoid the runtime cost of that. And there's a bunch of other things that are other examples of zero-cost abstractions here as well. Like in Java, we do type erasure for generics. This has some runtime dispatch cost. In Rust, it's more like C++. The compiler's effectively copy-pasting the generics code. Traits, which are interfaces in Rust, these have static dispatch by default, which means you don't have to jump through vtables at runtime. A very small cost in most domains, but one that Rust wouldn't accept because it adds cost. And there are some other interesting ones. Option and result are core types for modeling nullability and fallible functions, and they have some cool properties. In some cases, they don't require any allocation on the heap at all, so you can wrap something in a result and it stays on the stack if you're wrapping a primitive. And in some cases, they don't even add additional storage around the thing they're wrapping, which is pretty cool when you think about it. And this isn't exhaustive. This is just to kind of give you a flavor of what Rust is going for when it makes language decisions. And if you've spent any time on Hacker News or the internet or at your local nerd pub gathering, people in the Rust community can be extremely over the top with their enthusiasm for the language. And I can as well. I think this is good fun. I think it also puts people a little bit off of having an interest in it, especially if you've been working in a language community that's been incredibly productive for decades at this point. So it's kind of cool to look at the languages like with a bit more of a focused attention to detail. Like, what does this actually bring when we strip back the hype, which I'll try and go through a bit today. And full disclosure, when I wrote the proposal for this talk, I didn't really expect it to get accepted at DevOps and Java conferences. And it turns out, in retrospect, if you write a talk and you say, I'm going to have 10 of these and 5 of those, and you try and squeeze it into a 40 or 50-minute slot, it's really hard to make that talk not suck. So rather than doing that, and I hope I don't disappoint anyone too much who really wanted a listicle for this, I've kind of broken things down into some different deep dives into interesting parts of the language and arbitrarily awarded points either way based on what I think is important. I think this works better, but if you really, really wanted like 15 things, come and harangue me afterwards and I'll apologize deeply. Cool, so let's get started building our silly tile service thing. First off, we need to pick a stack, and I am an enormous Quarkus fan, so the Java side of this slide is pick Quarkus, use Quarkus, it's great. You could pick Spring as well. I don't think it makes a substantial difference for the story today, but I basically just pick Quarkus by default for these things. On the Rust side, if you can imagine we're a new a Rust developer, you're basically going to be Googling and saying, what is everyone else using? And if you do that, you discover all these different frameworks and libraries and options that you have to compose yourselves, right? You don't know what to pick. All of the kind of feedback on the internet with Rust things tends to be really, really performance-oriented, which isn't so helpful, I think, when you're trying to work out what a popular ecosystem is. So you can realistically go and jump on crates.io, which is the equivalent of Maven Central, and say, hey, what's actually popular? And you end up with a set of decisions that looks like this. Axiom is the web framework, SQLX for database access, and a few things for observability. And the observability part is a bit confusing, and I think we can do better. And as somebody who works on OpenTelemetry Rust, I would like to do better. So I've kind of got a section later on about what works there and what doesn't and how we're going to try and improve it. On the Java side, we use Quarkus. So we just add extensions for the things we need. We need database migrations, we need S3, we need all that good stuff. And we have a nicer bill of materials, right? It lines up all of our dependencies, all of our transient depths for us, and it's basically the Quarkus community coming to us and saying, hey, if you use these things, you are on the blessed path. You have a nice integrated ecosystem. Great job. On the Rust side, it's a lot more pick it and glue it together yourself. Lots of things are still pre-release, as you can see in the red highlighted text here. This is super indicative of the Rust community still to this day, even things that like massively underlie the ecosystem. It's kind of a fun joke to start with until you start trying to chase your dependency updates all the time with breaking changes, but it's manageable still. But overall, I think that if you start today and you pick one of these, you're just going to have a better time with Java. It's just much easier. You have these nicely integrated ecosystems. You have this real concept of a framework rather than a set of disparate dependencies. It's just better. The next thing we're going to do after we get there is let's actually build our application. And on the Rust side, it's pretty straightforward. We use Cargo. It's the tool that we use to interact with everything in the ecosystem. So it does our builds. It lets us format our code. Everyone uses the same formatter. This is very helpful. Lets us lint our code. Everyone uses the same linter. The linter can even fix lots of the lints for you. So you can say, hey, go and repair the ones here that you found that you can yourself, which is, again, very helpful. But we don't get very far up the application stack, right? We end up with something that prints hello world, and that's it. On the Quarkus side, we have a whole application. We end up not just with a thing that prints hello world to the console, we end up with a resource, it returns REST results, we can build things in Docker, we can deploy it, we can run it anywhere, we have hot reloading. We get much further. And then we have to look at how we actually start the application. Again, here in the Quarkus side, in the Spring side, there's just nothing. The framework does it for you, you don't consider it. In the Rust side, you have to start gluing things together. And I think anyone in here who's worked a bit with Rust before won't be too surprised about what's on the screen here, but I think it's interesting to pick through as well, because it starts to tell us a little bit about the language. The first thing that's worth noting is that Rust doesn't come with an asynchronous library. The standard library has the model for futures in it, so you can model futures, but you can't run them without bringing something else in. Most people use Tokio. There is other libraries in the community, but basically every Rust application you end up with today, you add Tokio, you bolt everything in. And that's a macro which transforms our main function into a regular synchronous main that can then go and invoke this async one. The next thing is that we have no exceptions in Rust. So whenever you have something that is fallible, that can fail, you have to model it explicitly in the return type. And I've set a bit more time aside later to talk about this because I think it's a really interesting decision in the way the language works. But the gist of it here is that we're saying main is fallible, it returns a result. If it succeeds, it returns the unit type, which is the 2 brackets, which is kind of like the equivalent of nothing. And we've used this popular library anyhow to elide or hide the failure type, but it can fail. And we benefit from that down here. We're saying, hey, load the application configuration, question mark means unwrap the result. If it succeeds, put it in config. If it fails, propagate the error up, which means main will panic, essentially. Down here, we see some asynchronous stuff. We can await a future. We can, again, unwrap the result of that. And at the very end, we can start up our web server. Not too hairy, but also already something you've kind of like had to bolt together yourself, and a few things that you run into straight off the bat with the async stuff. And then if we go, this is way too small for the slide. Can you roughly read this at the back? I saw some like semi-committed nodding, which is good. The point of this slide is to kind of point out that like aesthetically for writing code day to day, they are very similar. In both cases, we have the code that handles fetching a tile from a service. So I want a tiled piece of imagery, return the imagery for me. In both cases, we destructure the URL in the path. In the Java side with annotations on the path, in the Rust side with our URL destructuring. We pass the Y format, we fetch the tile set from our database, we fetch the tile from our database, and then we return a result. One thing that is worth mentioning here is that you in Rust always have the test in the same file. So further down in the code that contains getTile, you'll have this nested test module that pulls in all the symbols from above and then asserts on them. It's a small aesthetic thing. I think it's a bit nicer to work with because you always have everything you care about in one place. You also don't need to add extra testing libraries in Rust. It's all just built into the base ecosystem. But aside from those things, like quite similar so far, right? But what jumps out on the Rust side as well is where we are getting the things from that we need to connect to the rest of the world. So in Java, you would have your tileset repo, your tile store, and implicitly all of us know those have been injected into the class, right? Somewhere else you've got an annotation, it's injecting an implementation of an interface, and you just use them. In the Rust side, we have this state, app state, as the first parameter of the function. So we're passing in something from the framework that gives us access to the things we need to get tiles and to get our tile store. And if we have a look at how that works, it's interesting as well. Basically, what we have here in Axum is the ability to have an object or a struct that we pass into all of our handlers that the framework manages for us. We have to mark it as clonable because it can move across threads, and whenever you have things that can move between threads in Rust, you have to explicitly describe how they can move between threads. In this case, Axum is letting it move between threads by copying it. Derive clone is saying, hey, go and implement the clone interface for this automatically, please, compiler. And what we try and do in main with that app state we set up, with the database, the S3, and the config on it, is use it to set the state that we'll give to Axum, and then immediately format the bind address to open our HTTP socket. And if we do this, we run into our kind of first bit of rustiness, which is basically being told by the compiler, hey, you have this value, but I'm not going to let you use it twice. Using values twice is bad. Consider copying it beforehand. And if you're a Java developer or a developer from probably any other programming language in the world, this is a bit obscene to start with, right? You're like, I have values and I wish to use them in more than one place. Is this not reasonable? Why can I not do this thing? And the gist of it is that in order to provide static memory safety guarantees, Rust has this concept of the borrow checker. It imposes a set of rules on how we manage our memory. And by following those rules, the compiler can automatically say, hey, this value only lives for this long, so I can introduce the free statement, the bit that releases the memory for this in this place without ever making it memory unsafe, without ever freeing memory that's still referenced somewhere. So it's a bit of a pain to start with, and it seems rather silly because you intuitively expect to be able to use values multiple times. But once you get your head around the rules, it gives you this magical power, which is having automatic static memory management without a need for garbage collection and without a need for C-style freeze everywhere. And the rules go like this. Every value has one owner, and an owner is a lexical scope. So the body of a function, the inside of two curly brackets in a loop. When you assign a value to another name, the original value is gone. You can't use it anymore, which is what the compiler has just told us. But because we like to use values more than once, often when we program, we have this concept of lending a value out to something else. So if you write a function and the function needs to read a value but doesn't need to take ownership of it, you can make it type ampersand type name. It borrows the value, it returns the ownership to the parent scope. You're good. You can have lots of immutable borrowers of a value, but you can only have one mutable borrower. And this rule with a single mutable borrower is interesting because it also lets the borrow checker help us avoid data races in many cases. And the rabbit hole goes a little bit deeper with the borrow checker. Like, this is not a very long talk for going too deep on this, so I'm just going to give everyone a bit of a flavor of what it's trying to achieve. But in some cases, it's not really clear where the lifetime of a value comes from. So if you look at this function here, resolve format, we're basically saying, hey, here are two strings, I want you to borrow them, and if the first string is null, return the second string, otherwise return the first string. We don't want to have to pass ownership of the values into resolve. It doesn't make sense for it to steal the ownership from the calling function. And we also don't want it to have to copy the string when it returns it, because that would be silly. We just want it to return a value that has the same lifetime as the value that was passed in. But when we do this, the compiler complains. It's basically saying, hey, you've given me this thing, you were returning a reference, but I have no idea how long that reference lives for. I don't know its lifetime, so I can't guarantee the safety of this anymore. You need to help me out. And in this case, what we can do to help it out is to introduce a lifetime parameter, which is this generic looking thing, the tick A. And we're basically saying here, A is the name of the relationship. We tend to use single digit letter names for this for some reason. And it's basically saying the return reference will be valid as long as both of the input references are valid. So in plain English, the result is borrowed from one of these inputs. As long as they're alive, you can continue to use the reference to this. Substantially, this doesn't extend the lifetime of the value. So this doesn't change how long the parameter's passed in for. It just captures that information so that the compiler knows how long things can continue to reference that outside of the scope of this. And this isn't too gnarly so far, but it can get weirder. And some shapes are genuinely kind of hard to represent in Rust with the borrow checker. So for instance, self-referential structs. In this case, we have a struct that has int data i32, and then it has a borrow of a reference into that int data on it on my struct. And we can't write this in Rust ergonomically. We can't, with regular Rust, say, hey, this struct has a field, and then these other fields, they have the same lifetime as the struct. And the reason for that is that in some cases, the value, the struct itself can move in memory, and if we let you reference things on the lifetime of the struct, those values would be invalidated when those moves happen. So it's not on. If you end up in situations like this, you can use this library that everyone ends up having to use at some point called Ouroboros. If anyone knows how to pronounce that properly, please come and tell me afterwards. I've been practicing saying it and I'm still not confident it's right. But the gist of it is that there's some unsafe machinery that you can generate that makes this feel like it works reasonably ergonomically. It's very verbose to express yourself, but Ouroboros makes it a bit easier to do. This might seem rather abstract, but there are a few concrete cases where you would do things like this. A big one that we've seen at Datadog a lot is the idea of zero copy passing. So you have some buffer that you are passing messages out of. You have a struct that contains the buffer, but you also want to be able to read out the individual fields of it without having to copy them every time you have them. And you can use something like Ouroboros to model this without having to copy memory, which is really nice for hot path message passing. But it's getting pretty weird. It's kind of pushing at the limits of how the borrow checker works. And if we zoom back out from that to the problem we had, the compiler told us what we should do. We can clone config so that state can take ownership of it. Then we can use the original value still in line 8 to do the bind address. We can also think a bit harder and be like, well, format is probably just borrowing the arguments you give it. Format doesn't need to take ownership of config host and config port. So if we just reorder the function, this works as well. You have to think a little bit. The first time you run into these things, it's not very intuitive, but I think the learning curve has probably been overstated a little bit as well. The borrow checker is also good for data races. So on the Java side here, I have this kind of like classic trap for new players where I've got a hash map, and hash maps are not thread safe. And I've shared it between 8 threads and said each one of you insert 10,000 elements into it. And this will fail at runtime, right? It'll fail in a weird way because we won't get exceptions or anything like that. We just end up with way less elements in the list than we expect, in the hash map that we expect, sorry, because it's not thread safe, because we've used it inappropriately. But substantially, the compiler hasn't helped us with this. We require our own knowledge of the structures we should be using. We run into the wall at runtime. It's kind of like an insidious failure mode if you're not absolutely belting it with 8 concurrent threads. On the Rust side, if we try and express this naively, we get told you cannot do that because you're trying to take multiple mutable borrows of this thing at once, and that is not allowed. So we run into the wall, but we still have the problem. Like, we want to do this thing. The compiler says no. What can we do? And the first option here, and bearing in mind this is like a really silly use case, right? It's very hard to reason about what the proper way of doing this problem is to wrap the hash map in a mutex, so mutual exclusion, one thing can access the hash map at once, and then wrap that in an arc, which is a reference counting container that lets you share a thing between threads where all references to it are gone, it will free the underlying object. And then in our threads, we can lock the mutex, insert an item into it, and then unlock it. Obviously, this is going to be way slower than just doing it in a single thread, right? We have mutexes around every single item, so we have 80,000 mutex locks and releases or something silly like that. But the compiler has told us the original way is wrong, and we've been forced to think about how we want to actually model this. And we have other options too. We could say, hey, we want to have lots of concurrent readers, but one writer, and we can use a read-write lock around the hash map instead of a mutex, which is probably not going to help us here because all we're doing is having a lot of writers sync values unnecessarily into a hash map. Or we can use channels, which give us non-blocking send into the hash map from everywhere, and then have one consumer, which would probably make more sense here. But again, the takeaway is that the compiler says no, and then you reflect on exactly what you're trying to model, and you were given the concurrency primitives that you require to kind of think about that. And some of you are probably thinking, this borrow checking thing, it sounds kind of similar to escape analysis, and it does. Escape analysis, for those of you who haven't heard about it before, is this idea that in the JVM, when you have a function and you have a value that appears in the function and then is obviously freed in the same function, it never escapes the lifetime of the function. It's not passed out to other things or set on statics. The JVM can avoid ever putting that on the heap. It can just say, hey, this thing doesn't need to go on the heap. I can see that it's used very briefly. Allocate it on the stack. The GC never gets a hold of it. And that's true. There's like kind of this interesting parallel there. It doesn't get us as far as the borrow checker. It's not like a complete defense against the garbage collector, obviously. But it's a little similarity that I think is quite interesting. And there's this great article from Steve Klabnik, who is well known in the Rust community, that talks about escape analysis and the generational hypothesis of garbage collectors and borrow checking all in one big thing. I think it's really interesting. There's a bunch of links at the end of the talk. If you're into that sort of thing, I would suggest checking it out. And in this case, I think that both languages kind of get like a +1 for actually building out a thing to get started with. With Java, it's really easy, right? You use Quarkus, you use Spring Boot, you get going, everything works, it's all pretty normal. In Rust, you have more friction, but I hope you're starting to see that in some cases, depending on what you're building, if you're doing things where you're working with like intricate low-level concurrency primitives or like maybe HPC stuff, that friction is trying to add value. It's trying to pull misery that you might have in runtime forward into compile time. And it's easy to start seeing it as like, rather than just something where the compiler is unnecessarily frustrating you, it's something where the compiler is trying to push you in the right direction so that you have less adventure later on in your observability stack. And the next thing I want to look at is how we model data, because this is a great deal of what we do as programmers in our day-to-day lives. Imagine we have a data type that we need to model the different layers that we can have inside of our application. So like satellite imagery captured today, satellite imagery captured a week ago. In Rust, we never couple behavior and data, so we never have classes. We just have a struct, which is just the data. Here, we have two new interfaces we've automatically derived on it, serialize and deserialize. This gives us compile time generated JSON serialization. On description, we have option string. Rust also famously does not have null. It never committed the billion-dollar mistake. This is cool because it means that the compiler, again, always forces you to deal with nullability. So whenever you have code that tries to work with that description, you have to handle the null case. This is just how it is. Again, a bit of friction thrown up in your way, but it means that you have more confidence down the road that things are going to work well. There's a couple of other nice things in there. We have a wide swathe of numeric primitives, so you have unsigned 8-bit integers. You have a fixed length array of floating point 64-bit numbers for the bounding box, but like pretty Java-y otherwise, I would say. And if we look at the Java side, we would probably do it with a record to get a similar sort of flavor of just data, no behavior. We obviously have the description, which is kind of double nullable in the section that description could be null or the option could be none, which is weird to think about, sometimes useful, often not. Beyond that, like again, pretty similar. But what gets interesting is when we start trying to work with them. So in the Rust side, here we have some code that takes the tile set. It says, let's create a new derived tile set where we have changed the name to preview and otherwise takes all the same values, which is like the spread operator from JavaScript with a ... And then we can do structural matches across pretty much anything in Rust. And these will be exhaustively enforced by the compiler. So if you miss a branch for something, it'll say, no, you need to fix this. And here we're matching on both the outside tile set in the first branch. So we're saying when the tile format is PNG, extract the description and put that as PNG : into the label. And then we have a couple of other ones. You can do all sorts of fun things with the matches. It's pretty great. On the Java side, it's a bit more verbose. You end up in the same place at the end of the day, but you can't write it in such a succinct fashion. For instance, when we want to create the copy of it, we have to go and spread all the other values by hand. We could have helper functions to make this a bit easier if we wanted. Likewise, we don't have such nice structural matching yet. I'm sure it will come at some point because Java always catches up with all the other nice things languages do, I find. But it ends up a bit more verbose and a bit harder to reason about whether or not you've hit all the cases because the compiler can't help us so much. We're not saying, here is the structural thing we're trying to do. We're just kind of stringing together if things. It's a bit of an aesthetic thing, but I think it's just a bit nicer and easier to reason about the way you write it in Rust. The next thing that's interesting with data model is enums. So in Rust, enums are algebraic data types, which is a fancy way of saying that you can have values on the different variants. So here we're saying for JPEG and JPEG alone, we want to capture the compression level. And here again, we can do exhaustive matches across the top of it, which means that the compiler will tell us if we miss a branch. If I go and add a new tile format, all the code that depends on exhaustively matching that will fail, and I will have to go and fix it. In the Java side, you don't have ADTs on enums, but you can do it with sealed interfaces. So you can say, hey, this is a tile format, this interface that can only be one of these three variants. For the JPEG variant, we want compression, and then we can do exhaustive switch across the top with that with Java 21. So if we add a new variant and we don't have coverage for it, we catch it. So you can end up modeling a pretty similar thing. It's a bit more obtuse in Java, but it's a nice example of how the language really follows where other languages are going. And a thing lots of people talk about with Rust that felt really abstract to me to start with is this idea of decoupling behavior from data. So we don't have classes. You have structs, you have implementations of traits against the structs. If you look at it initially, like, okay, cool, I've got the implementation and the struct in the same file, there's just not in the same curly brackets. What does that even mean? And there's a couple of ways where you can really see the value this brings. The first is imagine we have a tile coordinate type that models the tile coordinates in our imaginary universe. And we have some third-party library that gives us geographic coordinates, like lat long, eastings, northings, all those good things. And we want to be able to model the conversion from any of those to a tile coordinate. In Java, we can't really extend that external library anymore. Like maybe we could try and hang another class at the bottom if it's the hierarchy isn't final. It would probably feel a bit weird. So what we probably end up with is some converter class with some static methods on it that does the conversion for us. In Rust, we have the from trait in the standard library. This lets us say, hey, compiler, if anyone ever wants a tile coordinate and they have a lat long, here is the conversion for it. And we can write our functions that need to consume tile coordinates in terms of anything that can be converted into a tile coordinate instead. And it just works. We've managed to extend this third-party library into ours without having to go and change the code in it. It's also worth mentioning that the way that this fetch tile is written here doesn't add indirection. If I just pass a tile coordinate in, it's not doing any extra conversions or anything. It's just working the way it was before. We've just basically loosened up the type system for the compiler's purposes a little bit. In the Java side, it's not a big deal, but we have to handle it ourselves, right? We have to remember how to do the conversions. We have to put them in where we need them. And again, we can magic this away with indirection a little bit, but it kind of shakes out of the box from the way that traits work in Rust. Another cool thing with the traits is that you can extend the language itself. So a bunch of the core language features are implemented in terms of the core traits. So iteration, for instance. You have a loop, you want to do a for loop, all you have to do is implement iterator for the thing you want to be able to loop over, and it works. You can also use filter, map, and collect. You've made all these core primitives in the language just work with your type by implementing one type iterator for it. And this is really nice. You see it a lot in libraries that you use. It makes everything much more expressive and much more consistent. So I'm going to go ahead and give Rust a point here, because I think I should. I think the types kind of end up being this thing that you can use to help think more thoroughly about your design, and it really comes a bit further than the Java model these days. I think Java will get there. Like obviously with the sealed interfaces, we're seeing Java pick up things that you can express differently in other languages. It's going in the right direction. But these days, Rust really feels more integrated. You can kind of tell that it's a language that's been written a bit more recently. So with all that said and done, let's imagine now that we've built kind of like this base of the application and we want to actually get it into production. So there's some pull request process, right? Like you go and say, hey, here's a PR into a monorepo, looks good to me. And our colleague Jeff comes back and he looks at this error handling we had in our tile handler and he says, hey, You were just panicking whenever you cannot return a tile. This is not good. This is not a way to do error handling. Please fix it or I will change my career and become a farmer, probably. And what we have so far in the base application is starting to help us get there. So we have getTileSet, which is retrieving things from the database. It returns either a tile set or a structured error, which returns things like, hey, the row wasn't found, I had an SQL error and whatnot. And then we have an equivalent on the storage error side for accessing S3. And we can go back to getTile and we can write it out in a really obvious way based on those errors. We can basically match across the response of it and we can say if it's okay, take the tile set out. If it's an error, DB error not found, return a 404, and so on. And there's kind of two downsides of doing it this way. The first is that it's obviously hilariously verbose. And the second is that there's no reuse. You can imagine that I go and add another endpoint, get tile set metadata. That first block is going to be verbatim exactly the same, but I can't benefit from that. And what you would typically do in Rust for this is implement an error that wraps up all the different errors that can kind of happen in the middle of your application. So here in the top bit, we have a couple of new errors, like you gave me a bad request, there was a validation error. And down here, we have two errors that are designed only to wrap those other two middle layer errors for us. So if you have a DB error, you can express it as app error DB. If you have a storage error, you can express it as app error storage. And that from annotation there is just generating the from trait for those things. This is cool because it means that suddenly if I write a function that has to deal with different parts of the API, I have an obvious error type to use for its return. I don't have to invent a new one. I just say this doesn't just return app error or DB error, it returns app error. And from there, I can go and implement something that maps from that back to a HTTP error. With Axum, you do this by implementing an inter response, and it's pretty much just the negative case that we saw in that overly verbose getTile function I saw before. Basically, if it's a bad request, return a 400, DB error, 404, and so on and so forth. And when we have these two layers of error mapping, we can go and write our getTile function like this. We say the error type is app error, so anything that can fail internally. When we call getTileSet, that returns a DB error potentially. Question mark unwraps that. If it fails, it turns that into an app error and that back into a HTTP error for us. So we have our error handling. We've been forced to write it exhaustively off to the side because of the structural checking of the compiler. And we can go and read our actual function in like the happy path fashion. In practice, this is really helpful because you end up in a position where you're forced to consider all of the different failure modes from the get-go. And once again, you're more likely to be like, this is probably going to work pretty well in prod. On the Java side, it's probably going to look like this to start with, at least if I wrote it. You would go and whack some things and catch blocks, and you would remember like, this could be a 400 or this could be a 404. You'll miss a bunch of it initially. You'll throw in a global exception mapper. That will turn the rest into 500s. And over time, you will go and add mapping for the other error cases you haven't really thought about. You'll get there in the end. You can handle errors in the same fashion, but the compiler hasn't been able to really come in and be like, here are all the conditions you need to consider. What I have seen happening in Java a bit recently, in some cases, is this pattern that some folks call sealed errors or functional error handling or error as a value. Basically, you can use this library Vaver, again here, please come and tell me afterwards how to pronounce this, to get access to the either type, to the optional type, and then rather than using exceptions, return a generic that either has the result type or the failure type, just like Rust, and then use the case matching across the top of that. So you don't throw exceptions, and you can be in a position where you're forced to handle all of the error cases just like you would in Rust. I think this isn't for everyone, but I quite like the pattern. I think it makes it much easier to write robust error handling code. It'd be cool if it takes off, in my opinion, but it's probably a thing lots of people have strong opinions about one way or the other. Anyway, in this case, I'm going to arbitrarily award Rust 2 points. I really think the error handling story is the best of any language I've used. It's very easy to be confident in the quality of the negative path in code that you write for Rust today. So having done that, we fixed our error handling. We're like, cool, this thing works. We're confident we've handled all of the different failure modes in exciting and comprehensive ways. Let's deploy it. And here, there's no... good work, whoever's in that room. Here, there's no Java side, right? You've got Quarkus, you build a jar, it even builds a Docker image for you. You don't have to do anything. You ship it, it runs anywhere. At the start of my career, this was a thing people talked about a lot because it was still kind of novel, like this idea of build once, run anywhere. You don't hear it so much anymore because everyone just expects it, right? We all use languages where that is the case, mostly. With Rust, we don't. Rust builds native binaries. And when we build on our macOS machine, we get a Marco ARM64 executable, which is not going to run in a Linux Docker container. But fortunately, Rust has a cross-compiler built in. So you can say, hey, Rust up, the Rust version manager, tell me all the different target architectures you support. You get these long, ridiculous target triples out. You find one that says unknown Linux and then a libc architecture. And you go and add it to your Rust build. And you say, hey, Cargo, can you build this, but do it for x86, 64, unknown, which just means like a generic Linux, and musl, so the musl C library as opposed to glibc, which is about what you would want for like a normal x86 Docker build. And this works sometimes, and sometimes it doesn't. The gist of why it doesn't in this case is that while the Rust has a cross-compiler itself, it doesn't have all the supporting infrastructure you need for native dependencies. For instance, if you have OpenSSL, my Mac isn't going to have a Linux AMD 64 musl copy of OpenSSL to link against. So it throws its hands up in despair, and you were promised this thing of nice native cross compilation. It didn't quite get there. And you have a few options. This happens in like every Rust project I've worked on. You think the cross compiler is going to save you, and it doesn't. The first is that you avoid ever having native dependencies, and this will get you further, but often you'll just add something later on, you'll get a new one. In this case, we ended up with OpenSSL because we use Rust S3, which has a dependency on that. We can swap it out to a Rust-only TLS library. This is fine. We'll run into something else further on. You can also use this cargo tool cross, which is an extra third-party thing that does the extra bits of the cross compilation for you. In practice, it works pretty well, but there's still gaps where it doesn't. What most people end up doing is pushing the complexity into their CI/CD pipeline. So you have a build, it fans out across all of your target things. You build it, it fans in again. You have to work more on GitHub CI jobs. I certainly don't like that, but it's robust in the face of adding other libraries. And if you want, you can also have this complexity with Java. You can go and build Graal images. Graal is super cool if you want to use less memory, for instance, which is useful in lots of cases. But you have a bunch of similar downsides. The builds are slower, like cargo builds. You can't deal with reflections, so automatically lots of libraries just don't work. Ultimately, you don't really need this, right? Like out of the box, Java, you don't even think about the complexity of building for production because it just works. So we've suffered through building the thing, and now we need to observe it. And this is obviously a thing that Datadog cares about a bit, so I care about as well. And when we push this out initially, we have no observability. We have our load balancer saying there are lots of 503s, maybe deal with that. On the Java side of things, we add OpenTelemetry. We point it at a collector. This could be Datadog, this could be Dynatrace, this could be all the open source stuff. It just works. Logs, traces, metrics flow out the end. It's literally that simple. And because we have a runtime, we can also do fancy things like plug in an agent. In the case of the OpenTelemetry agent or the Datadog agent, we can do things like do continuous profiling of your application. No code changes, just works. All very simple. With Quarkus, you can also plug in deb services, like this is cool, but how am I going to run it locally? Cool, Quarkus, go and spin up a container with Loki, Elasticsearch, and whatnot locally, plug it in there, and prod, point it at Datadog. Again, super straightforward. If you're using Spring, you're probably using Micrometer for metrics and probably Micrometer traces for traces. This wraps OpenTelemetry very well as well. You can just as easily push things out the back. You can do request correlated profiling. This is great. You can say, show me just the flame graphs from my get tile endpoint. And you can use flight recorder and mission control to get really detailed observability data out of the runtime. And to kind of put a line on this, like the observability story for Java is ridiculous. It's like clearly the best of any language that's out there. We are spoiled. On the Rust side, it's a bit gnarlier, and I say this as somebody that works on OpenTelemetry Rust. The kind of underlying tension here is that there are two libraries you need to care about. One is tracing, which gives you structured logging and in-application tracing, but not distributed tracing. There's another logging library called log, and you kind of think initially that that's the library everyone uses, but they don't. It's tracing mostly. And then there's OpenTelemetry to do the distributed tracing and metrics and get the logs plugged into it, because OpenTelemetry doesn't have its own log front end. You have to plug out something else in. And there's different ways of combining these. There's only really one right way. We've tried to make all the examples a bit better, but ultimately you're back in this kind of Rust thing where you glue it all together yourself and eventually you get on the right path, but it's not just as magic as with Java. The configuration, likewise, is rather complicated. You do it yourself. You get there in the end from examples, but it's not just like a paved path like with Java. For Datadog, we've just released a tracing library that builds on top of OpenTelemetry. OpenTelemetry has been designed to be extended, and it basically hides a bunch of complexity from our customers, which is cool, and I think we'll see this more from other people, but if you don't go into this vendor-specific way, you have to kind of glue it together yourself. So TLDR, Java observability is absolutely ridiculous. Rust, you'll get there in the end. It'll never be as good as with the JVM. The JVM is a very big advantage for observability, but it can definitely improve. Cool. So, does it go fast? I mean, I kind of started this thing off by saying like a reason you might use Rust is because of this perception that it's a quick thing. How does it actually look? Like, what do we have to do in terms of performance tuning? The first thing is runtime tuning. In Rust, this time, there's nothing. There's no runtime. You don't tune it. In Java, we have all of the ancient incantations that we are all either very entertained by or deeply terrified of. We can tune the memory. We can pick a GC. We can use crack to snapshot our running application and jam that into the Docker image as well. It's good fun, but it's all, for me at least, it's always a bit hit and miss to know what to play with. For Rust, we have no runtime. And there are some other interesting things that we might think about when we're talking about performance. So for instance, vectorization. You want to write some code that uses the CPU instructions available to you that does vector operations. You know, rather than doing one element at a time to add two arrays up, let's do the whole vector at once using AVX512 or what have you. In both cases, you can write code that looks vectorizable, and either the runtime or the compiler can lift that up and say, hey, this is vectorizable, I am running on a target or compiling for a target that has vector instructions, vectorize it. You have this pleasant surprise, it just works. In both cases, you also have a lower level API that lets you say, please vectorize this thing for me. The big difference here is like how certain this is to happen. In the Rust side, if you use the explicit vectorization APIs and you compile for a target that has those instructions, it's done, it's there, it works, it will never not work. In the Java side, you will never get vectorization out of the C1 compiler, it just doesn't, it's not interested in it. So when your code starts getting hot compiled, it can say, hey, this thing looked vectorizable and it'll automatically vectorize it. And if you use the lower level primitives from Jet 489, it'll probably do it. But it's more of a like, I will try very hard to do this, and less of a, I will certainly do it like with Rust. But the auto-vectorization in Java is really, really interesting. And like industry leading, again, I would say, insofar as I know about these things. There's this great video from Emmanuel from Oracle, who I discovered very recently lives in the same small Swiss town that I do, which is a bit random because we're not known for having tech experts. Not me, him. It goes really deep into auto-vectorization and how it works in Hotspot. It is a massive rabbit hole. It is super interesting. But if you're into these things, I would encourage you to check it out. And when we talk about Rust, another thing that people often mention is this idea of control. Like, I want to have low-level control of how things work, but kind of work at a higher level of abstraction as well. And a good way of highlighting one of the things that this enables is with this example of caching. So imagine we want to cache tiles that are recently used. You can imagine that we do imagery service for London. People are always going to be over Big Ben and the other fancy things in the middle. You don't want to go back to S3 every time for those, right? So you go and throw in a cache. You're probably just going to put it as a big application-wide cache. You're going to have some synchronization in there because it's being used across multiple threads. But regardless, it's going to be way faster, right? Like, you're always going to be paying less time for primitive synchronization in the runtime than going out to S3. So you're pretty happy with it. In Rust, there's this rather confusingly named pattern called thread per core. And it's confusing because if you use an async runtime, you always have a thread per core. But this is kind of like a more narrow definition of it. And the big idea is, like, if we have an input domain for our service that is really inherently shardable, if I can easily shard it across CPU cores, I've picked the zoom level here, which is not easily shardable. You're going to have way less requests for the high zoom levels than the low ones, so it's silly. But you can imagine you do it on the modulo of the x coordinate of the tile or something like that. What you can do is shard this across the cores that you have, and each core can have its own asynchronous runtime and its own cache that doesn't need any synchronization because you've done that. This also means that you can avoid data motion between the CPU cores, which is a really fine level optimization that avoids the synchronization of the cores between themselves, which saves nanoseconds mostly. In some cases, people care about this. The vast majority of this is a terrible, bad idea optimization because you'll end up with hot cores and cold cores. But it's something that you can model very idiomatically in Rust and kind of a highlight of things that this level of control gives you. In some domains, it's useful. In most, it's terrible. Please don't do this, is kind of the takeaway of this slide. So how do they actually compare? And there's heaps of caveats for this slide of numbers I'm about to show you. But the first one is really that, like, I benchmarked this with the load testing and the workload on my ridiculously overspec'd laptop. So it's not indicative of anything realistic. And I also went through everything after I'd written the code initially and profiled it and removed all the really obvious CPU bottlenecks. But what we end up with is that they're both about the same. And for anyone who's done performance-y stuff before, you know that this is basically telling you the latency of the services behind it, right? So they're both using SQLite, they're both using MinIO for S3 object storage. I've squeezed all of the bottlenecks out of them to the point that we're just seeing basically the time of talking to the backends. But the story to me is really that it didn't take much to do this. If you were a Rust maximalist, you'd be like, oh, Java's going to be rubbish. It's going to be way slower. There's all this overhead, you know, but the runtime is really, really good these days. And for normal use cases running under normal load, even things with a bit of a latency angle, like what I've picked here, it's pretty good. What is different is the memory usage. This is squeezed down to XMX 512 on the Java side. Obviously, the JVM makes use of what it has. So if I give it more RAM, it'll use more RAM and it'll garbage collect less. But it's very adaptable to the situation it finds itself, which is cool. Startup time on the Rust side, much quicker. We could use Graal and native image to push it down on the Java side. This would probably give us lower peak throughput, but more RAM efficiency. And we also end up with a much tighter little binary on the Rust side. So here, everyone wins. I think that the Java story, the performance is really, really good out of the gate. You don't even think about it anymore. The amount of juice you get out of a regular JVM without having to tune anything is frankly ridiculous. I think that in most cases where people are saying, let's use system languages to do this ordinary thing, it's probably being a bit silly. On the Rust side, you do have a lot more levers you can reach to when you need to because of this idea of low-level control that bubbles up to the surface of the language. So with all that said and done, it works. Like I actually built this thing. It's very snappy in both cases. Here is some OpenStreetMap imagery over the Berner Oberland in Switzerland. I'm not going to show you dragging around a map viewer because it's a bit silly, but if you're really enthusiastic, come over and have a look afterwards. So what are the big takeaways? For Rust, to me, it's really that the compiler is doing a lot for you, but it is pushing a great deal of complexity onto you as a developer. This tends to make your runtime life less exciting, which is generally good. But the initial developer experience is more frustrating. You get way less out of the gate with the application development experience as well. The error handling is also amazing. I hope I kind of conveyed that a bit, but it's fun to play with and see the classes of missed error handles that you avoid. That was a bad sentence, but I hope you know what I meant. On the Java side, the runtime is basically the star in the room, right? The runtimes are really, really, really powerful. Enormous amounts of engineering effort have been sunk into them at this point. This lets you write very expressive code without a lot of ceremony, and it will generally run very, very well everywhere. The ecosystem is amazing. The observability is class-leading. It's a great choice for almost everything. So what are you building? Like when does one of these make sense over the other? I think if you're doing typical everyday web services like most people are doing, and you have a company that's all in on Java and Quarkus and Spring, it's probably a pretty hard sell to want to use Rust unless you have like a real focus on resource efficiency, or you're just generally enthused about playing with new tools. I think that's also a reasonable reason to pick up a new tool. If you're doing a greenfields thing in a greenfields company, I think it's kind of 6 of one, half a dozen the other. You'll be quicker getting going with Quarkus, with Spring Boot, but you could get there with Rust as well. And even if you're new to the language, you're not going to suffer that much, honestly, these days. If you're doing things that are really resource constrained, embedded systems, things that you want to run in serverless environments like AWS Lambda, where you really squeeze down the memory usage and you want the startup time to be very aggressive, Rust is a great choice. And this is one I haven't talked about at all, but if you want to do code sharing between languages, so where you have some big block of logic and you use it in a bunch of different languages where you would be doing that typically over a foreign function interface. Previously, you would have to use C for this, and you would probably just throw your hands up in the air in despair and accept rewriting it for all languages because writing C is a miserable experience in all situations. These days, you can do it in Rust, and this is something that we do a lot at Datadog as well. For all of the different languages that we do distributed tracing for instance, we have this big block of shared logic for sampling strategies and all of that. This used to be duplicated per language, which meant that whenever we added new logic to this, we duplicated it per language and everything slowed down. Now we've put an enormous amount of effort into building this libdatadog thing that contains all of that and a nice ergonomic FFI bridge out of that for all the other languages, which has worked very well in practice. And that's it. I hope this was interesting. I hope some of you were like, oh, cool, Rust. I can actually go and play with it and I'm excited. Enjoy the rest of the conference and come and hassle me about anything.